So this morning we're going to start with something slightly different. We call it a What on Earth. And these are talks, lectures, which are related to drug delivery to the lungs, but offer a little bit of a twist, something slightly different. So I'd like to invite Leanne, come to the podium, please. So I'll introduce Leanne. Leanne Dailey is a pharmacist by training and completed her PhD at the Philipps University of Marburg on the topic of biocompatibility testing of polymeric nanoparticles for the controlled release of drugs to the lung. Leanne has worked at Nectar Therapeutics, now Novartis, and has followed that by positions at King's College London and is now at the University of Vienna. Her research has focused on the design of dosage forms for the delivery of anti-infectives to the lung, as well as the biocompatibility assessment of novel excipients for inhaled products. So Leanne, please give us an interesting and slightly different talk this morning.
Okay, thank you very much. I wanted to say that this talk is hopefully going to be enjoyable as the first session of the morning, because basically I'm going to be taking you through my holiday photos. Having said that, though, there is a little bit of method to the madness. And that was that when I moved to Vienna about 4 years ago, I met a clinical immunologist who is working in the area of allergy and allergic disease. And she was just putting together a big consortium grant to apply for funding to understand the effects of microplastics and nanoplastics in the environment on allergic disease. And they were mostly focusing on food allergies, but wanted to include an inhalation arm in their studies. And because, as Gary so kindly pointed out, I have a little bit of experience in inhalation and also a bit of experience in material science, including polymers. I also had an impinger, and I was willing to travel, and so I got the gig. And to be honest, I was quite surprised that we actually got the funding, and that culminated in what we now are calling the ImpTox project, which is one of 5 Horizon 2020 projects that was funded to investigate the health impacts of micro and nanoplastics on human health. And as I mentioned, our particular slant on this topic is to try to understand how environmental exposure to micro and nanoplastics might not only impact acute and chronic toxicity, but also allergic disease. And our core hypothesis about this is basically that microplastics, with their very specific surface properties, may be excellent adjuvants for different types of antigens, and therefore may impact allergic disease. And they can also be Trojan horses that can basically deliver chemical additives or heavy metals into the body and release them, thereby having a negative impact on health in this regard. So our project has started out looking at multiple aspects of this particular problem, including the inhalation aspect. When we started looking at designing a study to understand inhalation exposure to micro and nanoplastics, we decided we wanted to focus on very narrow questions. And one of our questions was, due to the rising levels of plastic pollution in our oceans, which we've all heard of and are aware of, does this mean that these plastics can degrade in the ocean into smaller and smaller pieces and eventually be part of the respirable fraction of sea spray aerosol, for example? And does this constitute a very special occupational health risk for people who work or live at the seaside? And do patients with lung diseases also still benefit from the healing powers of sea air or sea cures? Or do we now have a hazard in this particular scenario? In the same month that we actually submitted our proposal to the European Union, there was another study that was published looking at exactly this question. So we thought, hey, great minds think alike. Other people are out there thinking about this question. And so this study by a group of researchers went to the south of France and collected sea spray aerosols, both the fine particulate fractions using an active pump sampler, as well as the mist sampler or cloud water collector to capture mist droplets with a higher size range. And what they were able to do at the time was take the filter units from these samplers and using microscopy combined with FTIR, select specific particles on these filters, and then achieve chemical information through FTIR analysis. And at the time, this was about the best method for detecting microplastics in the environment and still remains one of the standard methodologies used. However, the limitations of this method are that it's a number-based method, so you have to actually physically identify the particles on the filter, select them, and analyze them. And at the moment, the resolution and sensitivity in terms of size of the particles is about 10 micrometers. Some people say 20, some other people say 5. But of course, this isn't really a relevant size range for respirable microplastics. And the further shortcoming is that it's an extremely time-consuming method, so it's not very high throughput. However, what did they find in this study? They found that there were 5 prevalent plastic types captured on this coastline in France, and they found about 2 to 20 particles per cubic meter air in the sea spray aerosol. The mean size was about 20 microns, but it ranged from anywhere, reported numbers of 5 to 140 microns in size. But based on this, they did a little bit of a back-of-the-envelope calculation, and they said that potentially 136,000 tons of microplastics could be released from sea spray over the course of a year. Now, in our project proposal, we decided that we were going to use a non-standardized aerosol testing method, actually from the pharmaceutical industry, so a method that we all know and love, and that is glass liquid impingement, to be able to size separate the aerosols on the coastline into a larger size fraction, an inhalable fraction, and a smaller size fraction, a respirable fraction. And we then decided to use a mass spec-based method to quantify the mass in each of these compartments to be able to get a better metric for these exposure assessments. So why did we think that a liquid impinger might be useful for this particular type of question? Well, first of all, it doesn't have any plastic components, or at least the one plastic component in there we removed. Secondly, as I said, we're able to separate the size of these particles according to their aerodynamic properties. And we did think at the time that it would probably be easier to extract these micro and nanoplastics from a liquid fraction instead of from a filter-based system, because we had heard that there are difficulties extracting micro and nanoplastics from filters. And finally, we implemented also what we call a granular bed filtration, which is we put ceramic beads in the bottom chamber to reduce the amount of splash in there, but also it has been shown that this can actually filter the incoming air to a much higher degree and have a higher entrapment of ultrafine particles down in size as low to 40 nanometers or so. So we took our impinger and we hit the road. Our first sample site was at a lake in about 80 kilometers from Vienna. We decided to use this as a control site because we thought that it would be a relatively pristine area, and we didn't want a lot of influence of air pollution and particulates from tire wear, for example, in this control site. And it was also close to Vienna, so it allowed us to practice a little bit before we left for the coast. So on a weekend last October, we took our impinger out to the lake and we sampled 8 samples of aerosols. This equated to 10 cubic meters of air. We pulled 60 liters per minute through our impinger, and we did this for 3 hours straight. And in between these measurements, we put a lot of procedural controls in there, which meant we filled the device, but without turning on the pump, then we washed it and collected the samples just to mimic the sampling conditions. For our sea spray aerosol measurements, we chose to travel to an island off the coast of Croatia. The reason that we chose this island was because, first of all, it was within driving distance from Vienna. Secondly, we have partners within our MTOX project who are running a clinical control about microplastic exposure in the area of Split, and we wanted to have a similar site of sampling. And then finally, because, hey, it's the coast of Croatia, right? So we went to Croatia and we set up our impinger exactly on the coast so that we knew that we could really, this was about 2 meters from where the waves were hitting the rocks, and we knew that we were getting a lot of sea spray aerosol here. And again, we did the same sampling technique of collecting 10 cubic meters of air and lots of procedural blanks. We have a weather machine out there so we can look at wind directions, humidity, temperature, and all these other aspects that might be relevant. We also had a control sampling site, which was about 100 meters back from the coastline, which was on that patio of the villa that we had to rent to do these measurements, as you do. Anyway, and so we had 6 samples there, as well as our procedural blanks. And when we washed the instrument to try to collect all of the deposited plastics, we decided that we were going to combine the mouthpiece and the upper chamber, and we're calling that our inhalable fraction. And then everything down below was the lower fraction. We're calling that the respirable fraction, where we should have, under these conditions, a size separation of anything in the respirable fraction below 6 microns in aerodynamic diameter. We freeze-dried all of the washings, and then we had to take our samples to Berlin, because one of the only methods to detect plastics on a mass base is using a special form of gas chromatography mass spectrometry, which is a form of pyrolysis GCMS, where you have to basically heat the samples to an extremely high temperatures so that they degrade, and then you characterize the degradation products. So we took our samples to Berlin, and there we did a lot of washing of the vials just to make sure we really tried to capture everything. And we sent the samples through the GCMS. Each plastic has a different level of detection and quantification, which makes it a bit more challenging. I'm going to say that most of the plastics that we were looking at had a limit of detection below 1 microgram. However, this is not true for all plastics. And now the good news is that just a few months ago, we got our first preliminary data from our Austrian samples, and we're pleased to see that we didn't find anything above our limit of detection. So if we calculate that back to cubic square meters, we found less than 0.1 micrograms per cubic meter air, which is great news for those of you who want to holiday in Austria. However, we did have one big hiccup, and that was we found actually quite high amounts of polypropylene in our samples. And as you can see here, when you compare the blanks to the aerosol samples, that the levels are very equal. And so this is very much indicative of a contamination. We found our source of contamination quite quickly because we had polypropylene lids in our sample vials. And you're probably sitting there thinking, you numpties, why did you use glass bottles with polypropylene lids? Yes, I know. Unfortunately, at the time, we were having distribution problems and we just could not source glass vials with metal lids. And we wanted to put off the experiments, but our project coordinator said, no, don't put off the experiments. We've got milestones to hit. So you go out there and it will be fine. And of course, it wasn't fine. But the key message here is that if you do read headlines about microplastics and nanoplastics in the environment, also in the body, in blood, in the lungs, I'd highly recommend that if you're interested, go into the papers and look at the amounts and levels detected in the procedural blanks, and you will see that plastic contamination is still a huge issue in a lot of these studies, as we found out ourselves. So I'm always taking some of the reports about microplastics in different compartments with a bit of a grain of salt. So where are we at now? We also were concerned that even though the TED GCMS limit of detections are quite low, we might not get a full recovery from our instruments. So at the moment, we're doing a lot of experiments to validate recovery from the impinger. We've also got samples from the seawater to measure to see if there was anything being sprayed up. We think we may need to actually pool some of our samples to actually get above our limits of detection. So we're going to validate that first and then finally look at the Croatian samples. So perhaps maybe next year I might have the results of this study, and then you can decide if you want to book your next holiday to Croatia. But until then, you'll have to wait. But I do have one final thing to report, because we decided not only to take our impinger outdoors, but we decided to go indoors as well. And we had a PhD student in an affiliated collaboration lab who was looking at additives in tire wear particulates. And she herself is an avid climber. And she was at the climbing hall one day, and she was thinking, well, you know what? Actually, in the climbing hall, I see a lot of dust from climbing shoes made of rubber with lots of additives in there. And this dust accumulates not only in the holds of the climbing wall, but also across the entire building. And it can get into the air. And so we decided to perform some aerosol sampling within the climbing halls to investigate whether rubber abrasion contributes to micro and nanoplastics in the inhalable fraction in these climbing halls. Now, the trick with this study is that we did not have the instrumentation to be able to measure the rubber itself, but what we were able to do is measure the additives in the rubber as a proxy for that. So we went to 2 different climbing halls within Vienna, and in this time, in order to make sure that we were well above the detection limit, we pooled the air samples. So we're sampling 50 meters of air, cubic meters of air, and we had our blanks. And what we found in terms of just the mass of the particulate matter in the air here is that the levels of particulates in these climbing halls are very, very high. They are much, much higher than the recommended daily limits that the WHO sets for a 24-hour exposure period. And this is actually something that has been observed in one other study in the past, so this is not unusual. The levels of inhaled particulate matter are both about the same in the inhalable and in the respirable fraction. And we saw that the climbing shoe sole abrasion was in both fractions because both fractions had black particulates in them. We then extracted the additives from these particulates using an accelerated solvent extraction method. And then we used UPLC mass spec to actually quantify 14 additives of interest. And you don't need to actually understand what those additives are, but 3/4 of them are vulcanization accelerators that are used in rubber manufacture. And then a few of them are also antioxidants and anti-ozonants that are used to create these high-performance shoe soles. And the one thing that we did observe when we looked at 30 different climbing shoes, because we took samples from climbing shoes, both old and new, is that the high-performance shoes were the ones with the most additives. And the shoes soles differ in terms of their structure and their flexibility depending on the performance level achieved. So what did we find in this particular sample set? We found that all additives were present in the powder of the shoe soles, which was primarily from the abrased shoes here. But what was kind of interesting was the fact that the chemical profile changes once that dust has been hanging around for a while and is aerosolized and actually is accessible to the lung. So we see a lot higher levels of oxidation products within this sample. And the amounts in the dust were pretty similar to the amounts in the respirable and the inhalable fractions. We did a bit of literature review to compare the amounts that we measured to other types of indoor and outdoor exposure studies for these particular chemicals. I'm just going to show you 2 comparisons right now. One is aniline, which is a vulcanization inhibitor, and we saw much, much greater quantities compared to other studies, whereas other types of chemicals are present in the climbing holes in lower amounts compared to indoor and outdoor samples. So at the moment, we're gathering a lot of this literature together and planning to publish this very soon. We need to do a lot more background and procedural controls within this study and look at the release kinetics of the additives under real conditions. And finally, start looking at toxicology and toxicokinetics of some of these additives, which aren't really well investigated. However, maybe one positive of the story is that we've had a lot of discussions with the Austrian Climbing Society, who is a sort of organization responsible for these indoor climbing halls, and they've taken this on board. So they want to try to reduce the particulates in their climbing hall by using liquid chalk instead of dry chalk to reduce the PM burden in general. And they're also starting to think about which types of shoes they might want to use as rental shoes in their climbing halls to try to reduce the burden of these other chemicals. So that's it for today. Thank you very much for joining me. I'd like to acknowledge all of the people who've been involved in the study design, and thank you for your attention.